You wake up, check your phone. GPS says you're 3 blocks away from where you are actually standing. Your radio cuts to static. The power grid shuts down. 6 million people sit in darkness. Satellites tumble. Astronauts hide. All because 93 million miles away, the sun just sneezed plasma at Earth. Space weather is not a metaphor. It is real, measurable, and it has ended lives and toppled grids. Solar flares travel at light speed. Coronal mass ejections carry 1 billion tons of magnetized gas. Radiation storms pierce satellites and skin. Geomagnetic disturbances rewrite the rules of electricity on an entire continent. Which ones should terrify you? What do they do when they arrive? How do we see them coming? That flash is a solar flare. X-rays and extreme ultraviolet radiation leave the sun and reach Earth in 8 minutes. No warning. The moment astronomers see the flare, Earth is already being hit. Those X-rays slam into the daylight side of our atmosphere, ionizing the D region of the ionosphere around 60 to 90 kilometers up. Normally, high-frequency radio waves between 3 and 30 megahertz bounce off higher layers and travel thousands of miles. But when the D region lights up with extra electrons, those waves get absorbed through a process called collisional damping. Radio goes silent. This is a radio blackout. On September 1st, 1859, British astronomer Richard Carrington watched the sun through a telescope fitted with dark filters at his private observatory outside London. At 11:18 in the morning, he saw 2 patches of intensely bright white light erupt from a cluster of sunspots. The flare lasted 5 minutes. 17 hours later, telegraph systems worldwide began failing. Operators reported sparks shooting from machines, papers catching fire, some lines working without batteries. Auroras appeared as far south as the Caribbean. Gold miners in the Rocky Mountains woke up thinking it was dawn. The Carrington event remains the most intense geomagnetic storm in recorded history, with a coronal mass ejection that crossed 93 million miles in just 17.6 hours. Typical transit time is 3 to 5 days. iScore data analyzed in 2024 shows the Carrington event was twice as large as any other solar storm in the last 500 years. A Lloyd's of London, an atmospheric and environmental research study from June 2013, estimated a similar event today would cost the United States alone $600 billion to $2.6 trillion, roughly 3.6 to 15.5% of annual GDP at that time. Also comment from which city you're hearing this from. Also, this script is researched and factual using sources from NOAA's Space Weather Prediction Center, NASA's Goddard Space Flight Center Heliophysics Division, peer-reviewed studies in the journal Space Weather, published by the American Geophysical Union in February 2024, and the British Geological Survey's digitized magnetogram records analyzed by Dr. Kieran Beggin's team in their April 2025 publication, showing the Carrington event saturated Victorian-era measuring devices. Now back to the information. Each letter jumps by a factor of 10, B class at 10 to the negative 7th, C class at 10 to the negative 6th, M class at 10 to the negative 5th, X class at 10 to the negative 4th, and higher. The scale is open-ended. An X28 flare releases 280 times more energy than an X1. On November 4th, 2003, sunspot region 486 produced what GOES initially measured as an X28 flare. But later modeling suggested reached X45. The detector saturated. This was part of the Halloween storms, 17 major flares between October 19th and November 5th. The X28 flare happened at 1929 GMT. The horizontal white streak across SOHO's ultraviolet camera shows where the sensor was blinded. That flare disrupted high-frequency radio across the daylight hemisphere for hours. Aviation and maritime operations lost contact. The ionosphere absorbed signals. Even VHF and UHF bands saw degradation. Minor radio blackouts classified as R1 on NOAA's scale occur about 2,000 times per solar cycle. They last minutes. X-class events bring R3 to R5 conditions lasting hours, knocking out transcontinental communication. When those twisted magnetic loops in the corona snap during reconnection, they do not just release light, they hurl plasma. A typical CME ejects billions of tons of solar material, electrons, protons, heavy ions, embedded in a frozen-in magnetic field stronger than the background solar wind. Speeds range from 250 kilometers per second for slow ejections to near 3,000 kilometers per second for the fastest. That fastest category can reach Earth in 15 to 18 hours. The CME that caused the Carrington event moved at roughly 2,400 kilometers per second, or 1.6 million kilometers per hour, and arrived in 17.6 hours because a prior CME on August 29th had cleared the path, sweeping away ambient solar wind. This concept of multiple CMEs creating express lanes is now understood as critical to extreme events. The March 1989 Quebec blackout involved two CMEs on March 10th and 12th. The first, from an X 4.5 flare, traveled at 760 kilometers per second over 54.5 hours. The second, from an M 7.3 flare, moved at 1,320 kilometers per second and caught up in 31.5 hours. Solar wind speed at peak storm reached 980 kilometers per second. The southward component of the interplanetary magnetic field, which determines geoeffectiveness, hit 40 to 60 nanoteslas. Normal is 5 nanoteslas. At 0127 Universal Time on March 13th, 1989, Earth's magnetosphere took the hit. 90 seconds later, Hydro-Quebec's grid collapsed. Quebec sits on the Canadian Shield, a mass of Precambrian igneous rock that conducts electricity poorly. When a geomagnetic storm rattles Earth's magnetic field, it induces currents in the ground itself through magnetic induction. In most regions, those currents flow through the soil. In Quebec, the rock resists, so the current finds the path of least resistance, the 735 kilovolt transmission lines. Geomagnetically induced currents, or GICs, flooded into transformers. Harmonic distortions appeared. Protection relays tripped in cascade. The James Bay network went offline in less than 90 seconds. The blackout lasted 9 hours. 6 million people lost power. Montrealers were trapped in dark office towers, underground pedestrian tunnels, stalled elevators. The Montreal Metro stayed shut through morning rush hour. Dorval Airport closed. Temperature that morning was near freezing. Across North America, over 200 power grid problems erupted within minutes. New York Electric lost 150 megawatts. New England Power Pool lost 1,410 megawatts and suspended service to 96 utilities. The U.S. had barely enough reserve. Auroras were visible from Texas to Florida. NASA's TDRS-1 satellite recorded over 250 anomalies. Space Shuttle Discovery reported a mysterious hydrogen pressure sensor reading that vanished after the storm. The March 1989 storm achieved a DST index, disturbance storm time, measuring the ring current intensity of negative 589 nanoteslas. Only a handful of storms in the instrumented era have gone deeper. Dr. David Boatler, head of the Space Weather Group at Natural Resources Canada, called it the archetypal disturbance for understanding solar-caused blackouts. Research published in Space Weather in October 2019 by Boatler shows the second CME's shock arrival coincided exactly with a substorm that hit the Hydro-Quebec system, indicating external triggering accelerated the substorm onset and produced larger GICs than expected. Hydro-Quebec spent $2 billion over 6 years upgrading the grid, raising trip levels, installing series compensation on ultra-high voltage lines, establishing real-time alert systems. Emmanuel Bernabeu of PJM, a regional utility coordinating electricity in 13 U.S. states, said in March 2021 that if the 1989 storm happened again today, Quebec would not lose power. The modern grid is designed to withstand a 1 in 100 year geomagnetic event. March 1989 was 1 in 40 or 50. Radiation storms are different. Solar flares and CME-driven shocks can accelerate protons and electrons to near light speed. These solar energetic particles race ahead of the CME plasma cloud. The fastest reach Earth in 30 minutes. They follow magnetic field lines, spiraling down toward the poles where Earth's field dips vertically. Energetic protons collide with atoms in the upper atmosphere, ionizing them and creating extra electrons in the D region. This absorbs HF radio at high latitudes. Polar flight routes lose communication. Passengers and crew at high altitude, where Earth's atmosphere is thinner, get radiation exposure. During a severe S3 or higher radiation storm on NOAA's scale, doses can approach or exceed regulatory limits. Astronauts face the same risk amplified. On the International Space Station, which orbits at roughly 400 kilometers altitude within Earth's magnetosphere, astronauts have some protection. During the Halloween storms of 2003, they still had to take shelter in more shielded modules. This had only happened twice before in the station's history. Radiation storms also damage satellites. High-energy protons penetrate electronics, flipping bits in memory. A single event upset occurs when a particle changes a 0 to a 1 or vice versa. If it hits a critical system, the satellite automatically enters safe mode. Stop all non-essential operations, point solar panels at the sun, wait for ground commands. During the May 10 to 13, 2024, G5 storm, the first extreme geomagnetic storm since Halloween 2003, NASA's ICESat-2 transitioned to safe mode because the storm disrupted attitude control. Aqua and Aura came within minutes of safe mode. Russell DeHart, Mission Operation Assurance Lead Engineer at NASA Goddard, sent warnings on May 9th after a NOAA alerted that a very strong storm might hit the next day. The storm compressed Earth's upper atmosphere, but also heated it, increasing drag on low Earth orbit satellites. Between May 7 and 10, 2024, satellites and debris in LEO were sinking toward Earth at 180 meters per day. Thousands of spacecraft fired thrusters simultaneously to climb back up. That mass movement created collision risks because avoidance systems couldn't calculate changing trajectories fast enough. This was the largest mass migration of satellites in history, occurring during what researchers from MIT called a new paradigm. 10,000 active payloads in low Earth orbit, most of them commercial small satellites. In 2003, only a few hundred satellites orbited Earth. Japan's Adios 2 satellite, launched in 2002, was destroyed beyond repair by the Halloween flares. The majority of satellites in LEO went offline temporarily. Luckily, no collisions occurred. Today, with vastly more objects in orbit, a repeat could be catastrophic. 3 massive sunspot groups emerged: regions 484, 486, and 488. The largest, region 486, measured over 13 times Earth's diameter. NOAA's Space Weather Prediction Center issued over 250 watches, warnings, and advisories between October 19th and November 7th. On October 28th, at around 1429 UTC, an X-17.2 flare erupted. A coronal mass ejection followed, moving at 2,125 kilometers per second. Forecasters predicted 24-hour transit. Actual time was 19 hours. Geomagnetic storm conditions reached G5 on October 29th. Less than 24 hours later, another X-10 flare and CME hit. The storm persisted for 51 hours. Then on November 4th, region 486 unleashed the X-28 flare, possibly as strong as X-45. This one came from the solar limb, so Earth caught only a glancing blow, but it still triggered moderate geomagnetic activity. Auroras appeared from Texas and Florida to Portugal, Spain, Algeria, and the Canary Islands. In Asia, sightings reached Turkey, Cyprus, Iran, northern India, and across northern China. Australia saw lights as far north as Townsville and Mackay in Queensland. Sweden experienced a 1-hour power outage. 12 transformers in South Africa, despite its low geomagnetic latitude, were disabled and required replacement. SOHO failed temporarily. The Advanced Composition Explorer satellite was damaged. Mars Odyssey lost its Martian radiation environment experiment. The DST index on October 30th reached negative 301 nanoteslas during the X-17 event, and negative 383 during the main Halloween storm. A second storm on November 20th hit negative 422 nanoteslas without reaching G5 classification. By comparison, Carrington event estimates range from negative 800 to negative 1,750 nanoteslas, and the EU May 1921 railroad storm is estimated at negative 907 plus or minus 132 nanoteslas. Region 3664 grew to 17 times Earth's diameter. On May 8th, it produced an X 1.0 flare and multiple M-class flares, each launching CMEs toward Earth. May 9th, X 2.25 and X 1.12 flares, both with full halo CMEs. May 10th, X 3.98. May 11th at 0123 UTC, X 5.4 to 5.7. Then May 14th, X 8.7, the largest flare of solar cycle 25 so far. At least 7, possibly 8, CMEs charged toward Earth. They arrived in waves starting May 10th, bunching together at speeds up to 3 million miles per hour, roughly 1.3 million kilometers per hour. Conditions were perfect. The CMEs' magnetic fields aligned southward, maximizing interaction with Earth's field. The geomagnetic storm reached G5, extreme, and lasted from May 10th to 13th. This was the first G5 storm since Halloween 2003, a gap of 20 years and 7 months. Auroras were reported at 26 degrees magnetic latitude, among the lowest in 5 centuries. In the US, lights appeared from Florida Keys to Hawaii, across the Yucatan Peninsula, the Bahamas, Jamaica, Puerto Rico. People in Japan, South Korea, northern India, and near Beijing saw them. Australia reported sightings from Townsville, Mackay, and Karratha. In the southern hemisphere, New Zealand, Chile, as far north as Concepcion. DEST index hit negative 412 nanoteslas at 0300 UTC on May 11th. Some readings suggested negative 518. The app index for May 11th was 271, the second highest ever recorded after November 13th, 1960, which reached 280. By another measure, the disturbance storm time index dating to 1957, this storm matched historic storms from 1958 and 2003. Reports of auroras visible at 26 degrees magnetic latitude suggest this may compete with the Lowest latitude sightings in the past 500 years, though scientists are still assessing. Dr. Dolores Knipp, research professor at the University of Colorado Boulder, noted technology changes make comparisons difficult. Aurora visibility allows comparison across centuries. Elizabeth McDonald, NASA heliophysics citizen science lead at Goddard, said the CMEs all arrived largely at once and conditions were just right to create a historic storm. Teresa Neves Chinchilla, acting director of NASA's Moon to Mars Space Weather Analysis Office, said we will be studying this event for years. It will test the limits of models and understanding. The May storm had a calculated return period of 12.5 years. Not rare, but severe. Data from JAXA's Arasi satellite revealed the most dramatic collapse of the plasmasphere ever recorded. Normally, the plasmasphere's outer boundary, the plasma pause, sits at 44,000 kilometers above Earth. During the May storm, it plunged to 9,600 kilometers in 9 hours. The plasmasphere is a protective layer of cold, dense plasma co-rotating with Earth, playing a crucial role in shielding satellites, radio, signals, navigation systems. Compressing it to 1/5 normal size allowed charged particles to travel farther along magnetic field lines toward the equator, producing those rare mid-latitude auroras. Ground-based GPS data showed the ionosphere responded dramatically. Total electron content, TEC, measures electrons per square centimeter in a column through the ionosphere. Background TEC in mid-latitudes is typically 50 to 80 TEC units. During the October 28, 2003, flare TEC jumped by 25 units, a 30% increase, peaking at roughly 100 TeQ. The enhancement lasted 3 hours, far longer than the flare itself, consistent with photoionization in the middle altitude ionosphere where recombination rates are low. The EUV portion of the flare spectrum is responsible. The November 4th and October 29th flares produced 5 to 7 TeQ enhancements. The Bastille Day X 10 flare on July 14th, 2000, also produced 5 to 7 TeQ increases. Amateur radio networks documented the October 28 flare's impact. The Reverse Beacon Network and Weak Signal Propagation Reporter Network showed near total loss of 14 and 21 MHz reports across Europe within minutes. 7 MHz, dark orange on frequency color codes, took the hardest hit. Radio blackouts across HF bands directly correlated with GAOS X-ray flux spikes. Collision frequency is high. HF waves get absorbed, collisional damping. An R3 strong radio blackout causes wide area HF blackout and loss of contact for about an hour on the sunlit side. An R5 extreme blackout, complete HF blackout, lasts hours. ICAO space weather centers are expected to provide advisories to airliners when flare intensity exceeds 10 to the -4th watts per square meter. That is X1. At 10 to the -3rd, that is X10, extreme advisories go out. On July 3rd, 2021, Sunspot region 12,838 produced an X 1.5 flare, the first X class of solar cycle 25. Frank Donovan, W3 LPL, reported American radio amateurs experienced sudden HF blackouts at 1429 UTC. The flare caused an R3 radio blackout. HF propagation blackouts are caused when X-ray and extreme ultraviolet radiation strongly ionize the absorbing D region. X1 flares typically degrade HF for 1 to 2 hours at mid and high latitudes on the sunlit side. X10 and stronger flares last most of a day and affect the entire sunlit hemisphere. Fortunately, X10 or stronger occur roughly once every 20 years. 95% of X-class flares occur when the solar flux index is 90 or greater. The remaining 5% can occur anytime. When that fast wind overtakes slower wind ahead, it creates a co-rotating interaction region, CIR. The compression zone produces geomagnetic storms, typically G1 to G3, less intense than CME storms, but longer lasting. They deposit more energy into the magnetosphere over time. CIRs are more common during the declining phase of the solar cycle. Earth's magnetosphere adjusts continuously to the solar wind. Pressure from the wind compresses the dayside magnetosphere. On the night side, the magnetotail stretches millions of kilometers into space. When the interplanetary magnetic field points southward, opposite Earth's northward field, reconnection occurs at the dayside magnetopause. This transfers energy and plasma into the magnetosphere, inflating the ring current and triggering substorms. The ring current is a belt of energetic ions circling Earth in the inner magnetosphere. During storms, it intensifies, creating a magnetic disturbance measured by the DST index. A DST below -50 nanoteslas indicates a storm. Below -100 is strong. Below -200 is severe. The most extreme storms drop below -300. Charged particles spiral along field lines toward the poles, colliding with oxygen and nitrogen atoms in the thermosphere at 100 to 300 kilometers altitude. Oxygen emits green light at 557.7 nanometers around 120 kilometers, and red at 630 nanometers above 200 kilometers. Nitrogen produces blue and purple. The auroral oval normally sits at 65 to 70 degrees geomagnetic latitude. During severe storms, it expands equatorward. The Carrington event brought auroras to 18 degrees magnetic latitude. March 1989, 25 degrees. Halloween 2003, below 30 degrees. May 2024, 26 degrees. These are extraordinary. Observers in Puerto Rico, at roughly 28 degrees magnetic latitude, reported seeing auroras on May 10th. In Jamaica, the Bahamas, northern India, central China, southern Europe, and northern Australia, cameras captured the lights. Human eyes often perceive faint auroras as gray or colorless due to the Purkinje effect. Rod cells dominate in low light but are less color sensitive. Modern cameras, even cell phones, pick up the colors easily. Social media exploded with images. This provided scientists with a massive data set. Aurorasaurus, a NASA-funded citizen science project led by Elizabeth McDonald, aggregates aurora reports and tweets into a verified map. Each verified report becomes a data point for testing models. The May 2024 event generated thousands of reports from latitudes where auroras are almost never seen. It also makes collision avoidance harder because conjunction data quality degrades. As atmospheric density fluctuates rapidly, predicted collision probabilities shift. An avoidance maneuver to reduce one collision risk might increase another. ESA simulated a Carrington-level storm during the Sentinel-1D mission campaign in mid-September 2025. The simulation modeled a massive X-45 class flare, traveling at light speed, disrupting radar, communications, and tracking data. Galileo and GPS went offline. Ground stations, especially polar, lost tracking due to peak radiation. Radiation levels surged, damaging electronics. The magnetosphere was hit by coronal mass ejection. Decision-making became a delicate balance under uncertainty. John Szymanski from ESA's Space Debris Office explained collision predictions become increasingly difficult to interpret as probabilities shift rapidly. The Halloween November 4th CME was underestimated in speed and geoeffectiveness. The May 2024 forecast was more accurate. No AA predicted arrival within 24 hours. Actual time matched closely. The most recent CME associated with the X5.1 flare on November 11th, 2024, was the most energetic and fastest of that sequence. Forecasters anticipated Earth arrival on November 12th. A G-force severe geomagnetic watch was issued for November 12th, with G3 strong for November 13th. This CME was associated with an S2 moderate solar radiation storm already in progress. The forecast was tough because the CME's ejecta aimed north and ahead of Earth's orbit, and previous CMEs were in the mix. Actual storm reached G4 as predicted on November 12th at 1850 UTC when the CME arrived. Solar wind speed hit 1,000 kilometers per second. Prior to impact, KP index was 2 or 3, quiet, 2 unsettled. During the storm, KP exceeded 7. ESA's SOHO and GOES-19 coronagraphs observed the CME about an hour after the flare. Initial speed was 1,500 kilometers per second. Solar wind. It provides 15 to 60 minutes, warning of CME shock arrival, sudden increases in density, total interplanetary magnetic field strength, and solar wind speed indicate the shock. Earth-based magnetometers detect the sudden impulse. Geoeffectiveness depends on the IMF direction inside the CME. If the field turns southward, reconnection at the dayside magnetopause becomes efficient. Energy pours into the magnetosphere. Storms intensify. The October 30th, 2003 storm had a southward IMF component of roughly negative 30 nanoteslas due to shock compression of pre-existing magnetic cloud material. That negative BZ drove the DST decrease. The March 13, 1989 event had BIS between negative 40 and negative 60 nanoteslas. For the May 2024 storm, the southward component was strong and prolonged. Multiple CMEs with southward fields compounded the effect. The November 11th to 13th, 2024 storms produced a GLE. High-energy solar particles can damage electronics on the ground if flux is extreme. They also pose risks to high-altitude polar flights. Radiation dose rates increase. Aviation authorities monitor space weather and adjust flight paths during storms. Cosmic rays, which are always present, decrease during solar storms, a Forbush decrease, because the enhanced magnetic field deflects them. Neutron monitors at Jangbogo Station in Antarctica and the Korean Peninsula recorded decreasing cosmic ray flux during the May 2024 G5 storm. The LEO-DOS radiation monitor aboard NextSat-2 observed increased total dose rate. Casey's all-sky cameras captured auroras in Korea for the first time in 21 years since Halloween 2003. At Jongbogo Station, both red and green auroral emissions appeared. Over the Korean peninsula, only red was visible, indicating emission from higher altitudes where oxygen concentration is lower, but collisions still excite the 630 nanometer line. After the Quebec blackout, Hydro-Quebec recalibrated protection systems, raised trip levels, installed series compensation to enhance grid stability, and established real-time alert systems measuring disturbances during magnetic storms. Other utilities at high latitudes, Scandinavia, Alaska, northern Russia, implemented programs to reduce GIC risks. In August 1989, another storm caused the Toronto Stock Exchange to halt when 3 redundant disk drives all failed. Since 1996, geomagnetic storms have been monitored from the Solar and Heliospheric Observatory, a joint NASA-ESA project. SOHO carries the Large Angle and Spectrometric Chronograph, LASCO, which images CMEs as they leave the Sun. SOHO also has the Extreme Ultraviolet Imaging Telescope and the Solar EUV Monitor. These instruments provide real-time data on solar activity. In 2013, the Federal Energy Regulatory Commission ordered the North American Electric Reliability Corporation to create standards requiring power grids to be somewhat protected from solar storms and equipment to be tested continuously. The concern is that utilities have failed to set adequate protection standards and remain unprepared for a Carrington-class event. NOAA's Space Weather Prediction Center runs models predicting CME arrival, storm intensity, and duration. Models ingest data from DSCOVR, SOHO, the Solar Dynamics Observatory, GOES satellites, and ground magnetometers. The WSA Enlil model simulates solar wind propagation through the heliosphere. It predicts CME travel time and impact angle. The predicted DST is calculated from solar wind parameters, velocity, density, IMF magnitude, and direction. Yet uncertainties remain. Small errors in initial CME speed or direction compound over 93 million miles. Magnetic cloud structure inside CMEs is hard to measure until arrival. A CME that appears Earth-directed from SOHO's viewpoint might miss if the eruption is slightly off-axis. The Halloween November 4th X-28 flare occurred at the solar limb, so the CME was not fully Earth-directed. Had it been centered, the storm would have been far worse. The May 2024 CMEs were well-aimed. Multiple eruptions from one active region increased the probability of geo-effective impacts. Active region 3664 was near disk center throughout its most productive period. Vigil will observe the side of the Sun from Lagrange point 5, unlocking continuous insights into solar activity not visible from Earth. L5 is 60 degrees ahead of Earth in orbit. Seeing active regions before they rotate into Earth view allows early warnings. SHIELD, another proposed mission, would sit farther upstream than DSCOVR, providing up to 2.5 hours advance warning instead of 20 minutes. Located more than 15 million kilometers from Earth, roughly 10 times farther than L1, SHIELD would see CME shocks earlier. This would give critical infrastructure operators time to prepare, shut down vulnerable transformers, reorient satellites, delay spacewalks, reroute polar flights. 2.5 hours can prevent billions in damage. The SWFO L1 spacecraft is en route to L1 now, scheduled to replace aging DSCOVR. Launch was November 3rd, 2025. SWFO carries advanced particle and magnetic field sensors. It will provide better measurements of solar wind conditions just before they hit Earth. The mission continues on schedule as of December 2025. The Miyake event in 774 to 775 AD was at least 10 times stronger than the Carrington event. Researchers have identified 7 similar events in the past 15,000 years. The largest solar storm on record occurred 14,300 years ago, found in tree samples from the French Alps. A 2022 paper suggests strong solar events could happen every 400 to 2,000. 400 years. Observations of sun-like stars indicate superflares far larger than Carrington may occur every few hundred years. Hugh Hudson's 2021 study in Annual Review of Astronomy and Astrophysics estimated the Carrington flare carried 4 times 10 to the 32nd ergs, equal to 10 billion 1 megaton nuclear bombs. Spikes of carbon-14 in 660 BC, 774 AD, and 994 AD may have come from superflares significantly stronger than Carrington. Hudson noted even the Carrington event is not detectable by the carbon-14 technique, so these ancient records are ominous. Earth had a lucky escape in July 2012 when a Carrington-class CME erupted, but narrowly missed Earth by roughly 9 days in orbital position. Voyager 1 and Voyager 2 both observed the Bastille Day 2000 event, making it the farthest detected solar storm in the solar system at that time. The X 8.7 flare on May 14th was the largest yet from that region. Mars lacks a global magnetic field, so solar particles directly impact the upper atmosphere, stripping it over geologic time. Understanding solar storms at Mars is critical for future crewed missions. Astronauts on Mars would have minimal shielding. Radiation from solar energetic particles and galactic cosmic rays is a primary hazard. Habitats must provide protection. Missions must monitor space weather and have storm shelters. The Moon also lacks a magnetic field. Lunar surface missions face similar risks. ESA is studying how regolith can be used for shielding and how biological effects from high-energy particles differ from low-dose chronic exposure. The Alara principle, as low as reasonably achievable, guides exposure limits. Crew schedules must minimize time outside during storms. In New Zealand, a transformer failed during the November 2001 storm, though New Zealand is mid-latitude. This 2012 study by researchers in New Zealand suggested storm effects can reach middle latitudes more than previously thought, not just high latitudes like Quebec. Submarine detection systems use magnetic signatures. Geomagnetic storms mask and distort these. Military operations get disrupted. On March 13, 1989, the Australian Army component of the UN peacekeeping force experienced problems. In August 1972, a series of flares and storms peaked with an X-20 flare producing the fastest CME transit ever recorded. A severe geomagnetic and proton storm disrupted terrestrial electrical and communications networks and satellites, with at least one made permanently inoperative. U.S. Navy magnetic influence sea mines in North Vietnam spontaneously detonated. False railway signals occurred in Russia during multiple storms. Erroneous blockages of tracks were reported for hours at a time on the Gorky railway system in 1989, on multiple dates in 2000, 2001. Telegraph disturbances in 1909 allowed the Perth to Kalgoorlie line in Western Australia 350 miles to work, with all batteries cut out for half an hour, concurrent with a visual aurora. This is not from direct solar radiation, but from loss of access to critical agricultural inputs. Society depends on electricity, communication, transport, manufacturing. A prolonged blackout cascades, water treatment stops, food refrigeration fails, fuel pumps do not work, emergency services lose coordination. The vulnerability increases as we become more interconnected. The 2008 National Academy of Sciences report on a Carrington-level storm estimated $1 to $2 trillion in damage, extensive social and economic disruptions. Recovery could take years, not weeks. Transformers have long lead times. Replacement capacity is limited. Multiple simultaneous failures overwhelm supply. Engineers would need to prioritize repairs. Some areas might wait months for power restoration. This is why grid resilience is now a national security concern. Space weather is not science fiction. It is operational threat assessment. The Global Positioning System has 18 satellites, but the full constellation is 31. Redundancy helps. If some satellites experience upsets, others compensate. Ground stations worldwide provide backup tracking. Communication networks have multiple paths. If HF radio fails, satellite links or fiber optics continue. The key is awareness and preparation. During the May 2024 storm, over 200 power grid problems in North America were managed without blackouts, unlike 1989. Clinton Wallace, director of NOAA's Space Weather Prediction Center, said more than 10 years of planning and preparation paid off. Early warnings and strong teamwork allowed operators to protect critical systems. Power, farming, satellites were ready. This proves preparedness is essential. Impacts can still be felt, like hurricanes hitting even prepared cities, but damage is minimized. The sunspot number in November 2025 dropped to 91.8, down from 114.6 in October, and far below the peak of 216 in August 2024. Specialists have not declared the maximum officially over. Solar activity can surge unexpectedly. Active region 4299, formerly 4274, returned to the Earth-facing disk in early December 2025 and produced an M8.1 flare on December 6th at 2039 UTC, associated with a full halo CME expected to impact Earth on December 9th, with a chance of G3 strong storming and a slight chance of G4 severe. The same region produced the X5.1 flare on November 11th, triggering a G4 storm. Fast solar wind from a coronal hole kept solar wind speeds elevated at 600 to 700 kilometers per second in early December. Another region, 4298, hurled jets and plasma throughout the day on December 7th. Much fell back, but some blobs escaped. These small eruptions amplify disturbances when swept up by faster events. The sun follows an 11-year rhythm, but intensity varies. Some maxima are quiet, some explode. Solar cycle 19, peaking around 1957 to 1958, was the strongest on record in sunspot number. July 1959 brought a massive flare and geomagnetic storm. We cannot predict which cycles will be violent. We track active regions, measure magnetic complexity, watch for flux emergence and shear. When a large, complex region rotates into view, forecasters raise probabilities. But the exact moment a flare erupts, the snapping of the magnetic band, is unpredictable seconds before it happens. By the time light reaches Earth, 8 minutes have passed. If a CME launched, we wait. Models run. Estimates are made. DSCO-VR sits upstream. When the shock arrives, warnings go out. 15 to 60 minutes. Not much time. Operators act fast. A grave was found near the White Sea coast, matching losses from a Norse saga. Dublin deeds price human lives in silver weight. Soil cores show longhouse heat storage. A boundary marker dug up where a warning post once stood. In 2014, researchers digging at the site of the Kew Observatory in London, where the Carrington event magnetogram was recorded, found the original buried baseline marker used to calibrate the instruments. The magnetogram traced by Balfour Stewart on September 1st and 2nd, 1859, saturated for 12 hours during the peak storm. The light beam swung off the photographic paper. Digitization of those records in 2024 by Dr. Kieran Beggin's team at the British Geological Survey revealed the magnitude was even greater than previously estimated. The paper archives were in relatively good condition, allowing reconstruction of the magnetic field variations. The horizontal component swung violently. The storm was not just a historical curiosity, it was a blueprint for disaster. September 1st, 1859, 11:18 a.m., Carrington saw white light. 17 hours later, Earth shook.